the fire burns brighter than the fire around you. And so if I was talking to my 5-year-old self, I would just have ran into that quote or came to that realization a lot sooner than later. So never giving up. Keep on going. It's going to get better.
Awesome. Awesome. And we have people still joining us, but we are live streaming now. And so anyone who has trouble joining us on Zoom can also watch on the YouTube channel. And it's just about that time. Let's give it just one more minute for folks who have joined us. Welcome. You're in the right spot. But while we're waiting for people to join, we thought we'd give everybody a chance to enter some things in the chat. For all of you, Ed and Diana and Hartzell and Joe and Jim, is there something about your life right now that would impress your 5-year-old self that you might be willing to enter in the chat? We would love to see it. Having your hair shaved, cool, very cool. Anyone else have something about yourself and your life today that would have impressed yourself back when you were 5 years old? Let's go ahead and let's do a couple polls as well. Climbing rocks for fun, being a doctor, yes. Awesome. Thank you. Getting your PhD within the next year, very, very cool. Let's go ahead and let us also do a poll here for you. So for everyone who has joined us so far, tell us a tiny bit about yourself. How would you describe yourself? As a planetary researcher, planetary engineer, a student or an early career scientist, an educator or an educator specialist, a professor, another scientist, something else. Working with the Mars rover, yes, even before the first Mariner flight to Mars, that is definitely impressive for adults, let alone 5-year-olds. So, and I'm going to give everybody 5 more seconds to finish answering. And while I'm doing that, Grace, can you go ahead and forward to the next slide, please? 4, 3, 2, and 1. And we've got a lot of planetary researchers with us, but we also have a number of students or early career scientists, a few professors, a few other types of scientists, and other physics students. Awesome. In Brazil, thank you so much for joining us, Diana. We're glad to have all of you with us here today for our Sharing Planetary Science seminar on common planetary misconceptions. And as you are going to see, there are other words that we are going to be using, but a lot of people have heard the term misconceptions before, so we thought that might be good to start off with. Let's go on to the next slide. And I wanted to share just a tiny bit about who we are. So I'm Christine Shupla at the Lunar and Planetary Institute, but we have a couple of expert speakers with us today. Sanlyn and Molly, would each of you mind just introducing yourself very briefly?
Sure. I am Sanlyn Buxner. I'm at the Planetary Science Institute in Tucson, Arizona. And I am an education researcher that works in planetary science. So I really specifically look at how people learn science and how we improve science for all different audiences.
Thank you, Sanlyn. Molly?
I'm Molly Simon. I'm an assistant professor at Arizona State University in the School of Earth and Space Exploration, but I focus predominantly on astronomy education research and looking into how students learn, predominantly undergraduate students in undergraduate astronomy classes, both in person and online.
Thank you. And so we are so grateful to have you both. Also with me are Grace and Sherelle and Yolanda, all helping out with this program. Grace, Sherelle, Yolanda, do each of you just want to pop in for a second and say hi?
Hello, everyone. I'm so happy that you are joining us today. My name is Sherelle Webb. I am the Public Engagement Lead at the Lunar and Planetary Institute, and I will be also taking all those questions from the live chat. So great that you're here.
Hi, everyone. I'm Grace. I'm an education specialist at LPI, and I'm running the slides today. Thank you all for joining.
And I'm not quite sure what Yolanda's connectivity is. Are you? I'm going to do a poll here to find out more about who's with us today. We've already found out that many of you, of course, are doing planetary research or professors or students. We've got a big variety. So what have you shared about? Where have you shared information about planetary science? So this is about engaging audiences. Have you given a public lecture before? Have you taught a college course? Have you done activities at an event? Do you present in a classroom? Maybe you've come and done something in a kid's classroom or an older person's classroom. Have you done something at an organization, a presentation, an activity, any of those sorts of things? Have you conducted an observing session or participated in an observing session or something else that you'd like to share about? We're going to give you 5 more seconds to finish selecting, and you can do as many of these as you want. You can pick all of them or none of them. 4, 3, 2, and 1. And so we've got a big variety here. A lot of you have done lectures and done presentations at organizations. Many of you have taught a college class or done something in the classroom, done activities, hands-on activities. Several of you have participated, about half of you have done an observing session. And feel free to add other things in the chat as well. Let's move on to the next slide. And we want to find out from you what you think misconceptions are. And also work and present at a planetarium. Awesome. Thank you. How would you describe what a misconception is? We're going to give everybody about 30 seconds to enter in the chat. What do you think a misconception are? What do we mean by when we say misconceptions? And Margaret has led field trips, so a big variety of experiences that you all have done and had. And while we're letting people type what they think about misconceptions, you're going to hear from Sanlyn and Molly in just a second about misconceptions and what they are. But yeah, factually incorrect view or a view that has some mistakes in it, misunderstandings. Great point. Great point. And thoughts that don't match reality, maybe. Yeah, and Sanlyn's nodding there. A wide held belief that is not correct. Like this idea, Lori, that vacuum sucks instead of just being a vacuum. Yeah. A misuse sometimes. Sometimes people use words in a way that that means something that's contrary to what the word actually is supposed to mean. Concept, not just a factual error. It's a concept. Good point, Bob. Commonly held beliefs that aren't necessarily true. Thanks, Jen. Let's move along to the next slide. And Sanlyn, it's all yours.
Awesome. Well, I'm really glad. This is such a great diversity of responses that I think is going to get at exactly the types of things we want to talk about. And so, when we think about misconceptions, 20 years ago, this was really where research was thinking about what do students have trouble with? What do they not understand? Right? We were really good at cataloging things that students didn't understand about things like moon phases and seasons and different things. And really, as we've done more research in education, we've done exactly kind of what Bob said. It's not about the facts they don't know. It's really about the underlying conceptual things that we hope students know. So can they think about models? Can they think about systems? And so really in the literature, when we do this kind of research that both Molly and I do, we don't really use the word misconception anymore. You won't see that in contemporary literature. You're going to see things like conceptual and reasoning difficulties, because we're really thinking about what are students struggling with? And again, really thinking about underlying ideas, not just some facts that they don't know. One of the things, and I'm going to do a really brief thing, if you would like resources on where this comes from, this is all from literature, we are happy to share all of that. We didn't want to bulk up the slides. But one thing to think about when we think about reasoning difficulties that anyone can have, students or adults, is that they can be robust, fundamental beliefs based on everyone's personal experience, from maybe things that are closer or hotter, right? All these experiences that we go through our life actually build up. And then we start to apply it, say, to astronomy or planetary science, and they can be deeply held. They may not even be really aware of the understandings, but they just know certain things. And we've all experienced, I think, that where students or young children will just tell us something, but it's from an experience they have. They may not always be informed by prior knowledge. They just may have thought of it all of a sudden. And so we'll start to think about some examples of this, and Molly has some great examples in their research. It may be transitional, which means it may not be internally consistent. It may change depending on the overall scenario that you have. And so there's just a lot of things to think about that they're not really thinking through everything, and they haven't really had a chance to think through everything. One thing I know both Molly and I talk a lot about is the one thing we do want to do, and this was a big shift again, is really thinking about moving from a deficit model. What do students not know? What are they not good at? And really thinking of an asset model of learning, and what do they bring to the table, right? And so we're not trying to fix people. We're really just trying to help them understand things that might be important or that they're interested in. Next slide, please. Perfect. And so this is like, right, we do years of education where I am on how people learn. But one of the most basic things is that, right, when we learn, we have to construct knowledge. Somebody can't do that for us. And so each one of us constructs our own knowledge. And so this actually came from a seminal work from the National Academies, which was called How People Learn, and says people have preconceptions about how the world works. That's our experience. If their initial understanding is not engaged, they may fail to grasp the new concepts and information. And so what's that saying is if we don't even ask students or people what they know or think, and we just try and pour more information on top of it, they're not even going to engage. And often this is the problem where you go, I told them, they just didn't get it, right? We didn't even start to engage what they know and what they're going to learn. And so we really want to think about how that might apply. How do we engage what our audience comes with to be able to work with those ideas? How people learn too, right? The second started to really help us think about not only do learners construct their own knowledge, right? But it has an interplay. What are they interested in? What are they motivated by? What are the things that they're bringing to the table? And so it's a complex system that we start to think about when we think about not only how people learn, but why they learn. And this will become important. Next slide, please. Some of the work that was done that's really important, we think about overcoming big issues, right? So like maybe our model of how moon phases work or other things, is that we know that a lot of this might be memorized, right? So there might be pieces that are memorized. There are things that are really held tightly, and that you can start to get a learner to become open to ideas if you can help contradict their understanding, if you can bring some evidence that makes them go, that doesn't work as well as I thought it was. I'm not able to use it in a way, but they have to actually become aware that the understanding or the model they're using isn't going to work very well. And so this takes a lot of time, right? This is very shortened, but when we think about, right, a lot of the work has shown us that they may take some of the knowledge that you are now giving to them and they might muddle it with the understanding they have. And so they might have some scientific information and then they kind of combine it with how they think about how the world or the universe works, and they have a new kind of weird model. And so it's one of those things where we don't fix people. We help people start to see how the universe works so they can start to come to their own understandings. And it's a real process. Next slide, please. And so we want to think about reasoning difficulties, and these kind of come in a couple different categories. And so one thing, again, when we kind of walked away from misconceptions, right, it's not always that people have a lack of knowledge or that they have the incorrect knowledge. It may be that they have never heard of or even thought about or engaged in a certain topic. And so we don't really think about reasoning difficulties about Bennu. They may not have even heard of Bennu, knows what an asteroid is. And so we want to think about they're just pulling information from something that it sounds like, or just any other experience. Now, there are things that we can start to address. Sometimes we just get words wrong, like a solar system versus a galaxy, or thinking about rotation and revolution. There are a lot of terms that people, again, don't really use a lot in their everyday life, and they kind of mistaken because they're not thinking about these things. But really, the kinds of things that we're all thinking about, and I think really matter to us, are models, right? So as they're kind of constructing explanations for how the universe works, that these are really hard to be able to address these models. And so again, day, night as a function of Earth's orbit, other things we start to think about, what is how they are thinking about this and how are they explaining it? Next slide, please. And so one of the things we want, again, we also are not going to just try and pour a lot of information, right? We want to really think about what are the big take-home points that we're hoping we can work with today, right? And so the first is audiences, whether they're students or undergraduates, the public, your audience is likely to create an original hybrid idea from your info and their info. So they're still going to have whatever understanding they came with. And they might integrate some of the understanding you came with, but that's just a reality of how we know people learn. And something I know that Molly's going to talk about is we want to be careful to make assumptions, even with really educated audiences. We don't want to assume that they have even really kind of baseline information. Again, not saying that they are missing things, but we want to make sure that we are building a foundation to help them really understand the kinds of concepts that matter. Next slide, please. And so we want to hear from you. What are the things? And we'll talk again a little bit about the research. And it can be topics, but we want to know what are the kinds of topics when you're doing these planetarium shows and these lectures and all these things. What do people struggle with when you're doing the kinds of engagement that you're doing?
And so we'd love to have you put things in the chat, experiences that you've had. Dark side of the moon. So this idea that the moon has a permanently dark side, is something that we hear. Distances and relative sizes.
Absolutely. Distances, relative sizes, timescales. Yep. Scale of Earth versus Jupiter versus Sun. Absolutely. Time and place and as well as process. Yes, absolutely. Not just facts. Probability and uncertainty. Absolutely. Oh my gosh. We see that everything, not just planetary science, right? We see that all the time. Terminology and jargon. Yep. So that's a really great point that jargon really is counterintuitive to the types of things that we have. So again, the vastness of space, science as a process, gravity, weightlessness in space feels like the metric system. Yeah.
And while you're continuing and finishing up answering your questions, I've got a poll here. How have you been surprised by a planetary concept that someone misunderstood? I'm going to give you about 5 more seconds to answer that one too. 5, 4, 3, 2.
Oh yeah, definitely switching scales, right? So really, really big stuff, really, really small stuff.
And no one said no. A couple of you aren't sure, but no one said no. Okay, Sanlyn?
Awesome. So this is really great. And when we think about being surprised by a misunderstanding, often as individuals that work with these topics all the time, right? We think about it all the time and we go, gosh, that just seems so obvious, or it just seems so clear to me. But one of the things we always have to remember is that it is not clear to many people who are not thinking about these things all the time. Haven't had opportunities to think about it or really have someone sit down and explain it. Next slide, please. One of the things we're going to start to talk about, and everyone is doing such a nice job really thinking about this, so wonderful, is that, again, early research showed us that, students, even college students, don't understand lunar phases or seasons well, right? And so we were really good at cataloging. We used to catalog this, right? The things they don't know. But what we want to think about is the underlying cause, right? So that really students and the public, they're really struggling with spatial relationships, how things are in space, absolutely size and scale. Many people talked about that. And orbital shapes as well that might lead to some of these misunderstandings. And, we as educators, textbook authors, anyone who puts out graphics, we actually introduce some really spectacular incorrect ideas that can then even lend themselves to conceptual difficulties. So a really classic one we always talk about is the orbits of, right, just looking at the orbit of the Earth and why there are seasons. And it, they might have an idea about closer means hotter, but then when we look at how highly elliptical we make that in a textbook, we are really good at doing some non-verbal, kind of emphasis, right, that leads to some misunderstandings as well. And so these are things to be aware of, the things that we do as educators. And so we do notice that many people struggle in understanding planetary systems in general. They're not understanding our own planetary system. And so when we ask them to think about exoplanets and other exciting things, because we think, wow, it's really cool, we want you to understand all these new exciting things in the news, we still know that we have some fundamental understandings that aren't totally there. Okay, I'm gonna look at the comments and then Molly, I'm gonna have you go. Okay, Lucy says, oh, great. I find that when I'm learning something new, I have to put it into a context that is relevant and important to me. What a perfect point, I think, for everyone, right? And it's best if I can relate it to something I know about already. And so that's exactly right, that you're layering your understanding on something that you already have. And I think what a great model for when we think about how everyone is learning. That's great. And then, yeah, Margaret, need to include perspectives. Where are you when you observe something? And I think many of us don't even get that far to think about where you're thinking about being. And so a lot of these things about relative, lots of things people struggle with. Okay, I'm going to send this over to Molly so she can talk about some of her work.
Okay, great. Can we go to the next slide, please? Okay, so I want to just bring up some of the results that Christine already actually had in her data that I actually confirmed with a study that I did way back when I was a grad student, way back when in 2017. And this was a study of about 1,100 college students enrolled in introductory astronomy courses. And they had to answer one of 6 short answer questions on the topic of planet formation and solar system, and then some of the relevant concepts therein. So gravity, basic definitions, and many of the conceptual and reasoning difficulties that came out of that effort were really in line with what Christine had already had when she was preparing this workshop. So it just kind of was further evidence that this was actually existing in the data for college students. So I remember that one of our participants said that their students often had difficulty with gravity. And in our data set, we found something analogous. And we actually found that problem understanding gravity, even it could be traced back to a misunderstanding about density and mass. So as astronomers, we throw out the terms like more massive, more dense all the time. And we assume that our population has a general understanding of what these terms mean. But a lot of students actually conflate the terms mass and density and think that higher density means more massive. And they do this without taking volume into account. And then this has implications for their understanding of the role of gravity, and they misapply the gravitational force law because in the numerator, the mass of the object and the mass of the star is part of the equation. So the biggest example that I got in my data set was that students thought that the terrestrial planets were actually more massive than the gas giants because they're more dense, and that they experience or have more gravity than the gas giants. And that's what keeps them closer to their star. And so it's very important when you're introducing terms that you may use all the time when you talk to other scientists, that your students may not have a good understanding of what these general terms actually are. And then that can increase their conceptual and reasoning difficulties when you introduce terms that build off of these more general terms, like gravity, which builds off an understanding of mass. So we can go to the next slide. So scaling systems, there were so many people that mentioned this when they brought up some of the misconceptions that they've encountered with their either their general public or their students. And we found this most definitely in our student data. So most students don't know how big or far away planets are. They don't know the difference between the solar system and the galaxy. And what I found that was really interesting that I totally took for granted as someone with a background in astronomy is that students believe that the solar system consists of multiple stars. And the biggest conceptual and reasoning difficulty was that the constellations that we see in our night sky are part of our solar system. And it makes total sense to me why a student could think that, because we can see them from planet Earth. So students don't understand how massive these stars must be, that we can still see their light, despite the fact that they are many, many light years away, so often in most cases. And that constellations and star parties are some of the most accessible ways for the general public to get involved and to learn about space. But a lot of times the people in charge of those star parties don't think to say the constellations that you're seeing are not actually in our solar system, because we just make the assumption that our population knows that. So that was really interesting for me, one of the most interesting findings, because I totally took that for granted as a practitioner and as a graduate student, that the public could think that these constellations were actually part of our solar system. So next slide. There are also issues with astronomical and geological time, and this also parrots what many people brought up in the chat. So most people have no idea how long ago the solar system formed. And in part of my graduate research that I was just talking about earlier, the most common misconception from the data set, hands down, nearly 44% of these 1,100 students attributed solar system formation to the Big Bang in some capacity. They were not able to differentiate the formation of the universe from the formation of the solar system. And what's really interesting in this Wallace paper that I cited here after my own paper was that in that paper, they actually talk about how students believe that the Big Bang occurred from pre-existing matter. So there was something that existed before the Big Bang, and that pre-existing matter acted as the catalyst for the Big Bang. So not only do they have this conceptual and reasoning difficulty about what the Big Bang is, they are completely off base when it comes to cosmological time. And we see this all the time, maybe even more egregiously with geological time, how many students and the general public don't realize that in the scale of cosmological and geological time, humans have only been on the planet for such a small blip of that. And they really think that the separation between humans and the dinosaurs is not that significant. And so emphasizing, the difference between these timescales and how epic these timescales really are is critically important when you're lecturing to a general audience or teaching a general astronomy course. All right, next slide. So this was also something that was a little bit more niche because the questions were geared more towards planet formation, but it's still really important, which is that students don't know how hot or cold the planets are. They attribute their basic understanding of colors as like red being hot to thinking that it's the same for the planet. So they may think that Mars is very hot because it's red, and they don't actually realize that it's the chemical composition that's making it red. And they don't realize that the gas giants are predominantly, yes, they know that they may be predominantly made of gas, but they don't realize that there's the structure of rocky and icy material in their core. So that there are many different compositional factors when you're looking at Jovian planets. Also, what I found in my particular data set was that students believed that just the sun's heat was solely responsible for determining the composition of our planets, but they don't have an understanding that it's really the condensation temperature of the elements at a planet-specific location where it's forming that determines what it's predominantly going to be made of or how large it's able to grow. And condensation temperature is maybe something that's slightly more advanced, but there have been many curricular materials developed recently that have made this concept more accessible to gen ed audiences with a great success and the public. So I guess the next slide. I think Christine, this one is yours.
So also with planetary science, there's also this emphasis on planetary exploration. And there's a lot of misconceptions. There's a lot of initial knowledge and ideas that are influenced by what they see in science fiction and movies and books, where a lot of people haven't differentiated what they're getting from media and whether it is actually true going on right now versus it was a movie they saw. So many of them, most people do know that we went to the moon. They don't know how recent it was. Some of them think that we went there last year. Some of them think that we have people there right now. So they're a little confused about when we went and not realizing that it's not happened since Apollo that we've sent people there. If you talk to people, you will find that a huge number of people, kids and adults, think that we have sent humans to other places. They think that people are walking around on Mars. They think that that movie and the book about Mars are true and based on fact. They think that they assume, based on what they've seen, that we have gone so much farther than the moon in terms of people, not just spacecraft. And they think that all spacecraft that we send out there, the rovers, come back to Earth. So when they find out that we have, rovers and objects that we've left behind on the moon and Mars, they feel bad for them because, of course, they've anthropomorphized them. So they feel bad about that. So when you're doing an activity about, say, Mars exploration, you can't assume that everybody knows that we don't have people there, because a lot of them might be thinking that, depending on the audience, for instance. And they don't understand what the big deal about a sample return from Mars is, because they think that all of our spacecraft come back. It hasn't occurred to them that we leave them there, that we abandon them. Anyway, great points. Let's next slide, please. And also in terms of planetary science, there's a lot of ideas about geology that are born of terminology where people are just unfamiliar with certain concepts. The most common term for granite that people are aware of, they're used to thinking about it when it comes to kitchen countertops. However, they label everything granite, right, for kitchen countertops, regardless of whether it's granite or gabbro or something else completely different. So they think any type of rock with large crystals is granite. The composition means nothing to them. And if you go deeply into things like sedimentary, igneous, metamorphic, many of them might have trouble remembering the difference between these different processes, and they don't know any of the rock types. They may have heard of schists, they may have heard of some of them, but they don't really know what that means. And the other thing in terms of planetary science that you often hear people talk about tectonism, and the average person only hears that term as it relates to plate tectonics. So when you start discussing tectonic features on Mercury or the moon, they might assume that you're saying that the moon and Mercury have plate tectonics, just because you're talking about tectonic features. So again, terminology, they're latching onto that one word that they've heard of before, that they learned in 6th grade, and everything that they know about it. So next slide. So we're back to you folks here, and we've got some great comments here. How do we address these? And we're going to have some exercises for the last half an hour. But first, we want to hear from you. What are some of your ideas? What have you tried before to address some of the misunderstandings that your audiences, whether they be students or the public or whatever, might have had? And while you're thinking about that, please feel free to type in and enter your thoughts while you're doing that. So there was a comment about, timelines and people thinking about if the Big Bang is the formation and how the Earth forms. There's confusion there. They assume that the Big Bang made the Earth instead of the Big Bang made something that became the Milky Way, that then eventually made something that became the solar system that included making the Earth. They just kind of go directly from one to the other. Margaret, your points about astrobiology can be very challenging. So we also have to be aware that some of what we're talking about isn't necessarily just challenging terminology or building upon their prior knowledge. We're also potentially interacting with people's religious views in some cases as well. So ideas, while we're waiting for you all to enter, please enter your ideas. What have you tried? So Louis, thank you so much. Providing maybe a concepts and terminology list to help clarify those terms. Yeah, great point, Erica. There was more time between the Stegosaurus and the T-Rex than there was between the T-Rex and us. Great point. So this idea of some sort of a comparison.
I actually have a colleague who wrote a paper, Sanlyn, this was Lacey's paper, that said it was called Stegosaurus and T-Rex Never Met. And then it was a paper about cosmological and geological time and the misconceptions. So that's an interesting one.
It is. The Roman Empire could have fallen 1,000 years in that time interval. Repetition. Repetition can absolutely help as long as you're not just, as long as you're capturing their attention, engaging them, absolutely. So from a sentence that opposes the misconception and use that sentence over and over again. So, there is one star in the solar system. There is one star in the solar system. There is only one star in the solar system. Out of all the stars in the galaxy, only one of them is in our solar system. Absolutely. All the planets stacked end to end fit between the Earth and the Moon. So giving them a visual, awesome. I like that. With the solar system and universe timeline going forward to the next 10,000 billion years. And by the way, they have no idea that GYAR is billions of years. And present the progress of time, not just the endpoint. So not just where we are right now, but how time progresses. Awesome. And if students give an answer that isn't factual, give them respond in terms of how we learn from incorrect hypotheses. I like that a lot, Margaret.
These are all really good ideas.
Shall we move on? Next slide. And I think this one is Sanlyn's.
Cool. So let's think about promoting our understanding in a short interaction. So we might say, I'm at a science booth, or I'm just talking for a few minutes, right? So just the time that they're kind of coming by. And so one of the things we like to say, don't assume knowledge. You can't go too introductory. Again, jargon's not going to help us in this case. Asking questions to elicit their own ideas. You'll know a lot more if you start asking what they know. And we want to think about maybe more than one way to convey what you want to communicate. So demonstrations, visuals, not just kind of talking. Using their bodies kinesthetically, perhaps. Lots of different ways to do these things in short interactions. Again, we want to say to be careful with our language so that we're using words that may not be easily confused as we kind of think about it, and really using kind of the more basic language to really help. Again, we're saying be careful with our graphics. You don't want to overly exaggerate anything. This one's really important, right? Being respectful of your audience lived experience, right? Certainly no one wants to feel badly when they're talking to a scientist that they don't know something. And so just being super respectful. And we're going to have a scenario where you might, we might have some discussions about what that looks like when you start to have people who don't even believe in the types of things we do. And I think something that's always important is going with the audience interest. If you have their attention for a few moments, really figuring out what they're interested in and going with that. And so here are just some tips, as it were, to help us think about how to do this. And then Molly, get to talk about our longer term interactions.
Okay, that'll be on the next slide. So in longer interactions, we're thinking if you're giving a longer public talk, or if you're teaching a gen ed astro course or planetary course, something where you have more time with your audience. So many of these tips are repeated, which is don't assume knowledge again. You can never get too introductory. Another thing is depth over breadth. I can't tell you how many times in general astronomy courses, geology courses, planetary courses, we try to teach pretty much everything in the textbook. And in order to really hone students' knowledge and understanding, it's so important that maybe we focus in on 3 or 4 topics and just do them really well. Like have an entire intro astronomy course dedicated to galaxies and stars, or another dedicated to planets in the solar system and beyond. And instead focus on students really leaving those courses with an understanding of the material that was taught. Once again, asking questions to elicit your audience's ideas and to help them come to the correct conclusion on their own, whether or not they speak with peers or people around them, and then kind of confer on an answer, or giving them a chance to work through things before we just blurt out and tell them the way that we think of something. In lectures, we don't want individuals to critically examine their own prior knowledge. So the reality is some of these misconceptions and misunderstandings will be really deep-seated. Again, it just depends on a person's lived experience. You can really only do the best that you can to ground students' thinking into what's most scientifically accurate, but you're not going to be able to reverse, 18, 20, 30, sometimes even 50 years of lived experience. So being empathetic to that lived experience and careful with language is really important. And that's why it's great to find more than one way to convey what you're communicating, and just to really show empathy towards people who may have different belief systems than yours. And then another specifically for classroom use is to use active learning strategies like think, pair, share questions. So think, pair, share questions are really questions that are used to kind of hone in on exactly where students' misconceptions are coming from. And students answer a question, and then the instructor prompts them to speak with their neighbors and talk about their individual perspectives. And then they're asked the same questions. And then there's a discussion about whether or not their answers change after the larger discussion with their neighbors. Lecture tutorials are another fabulous educational resource. They are about 15 to 30-minute in-class activities that are meant to supplement traditional lecture, and they're written in student colloquial jargon. There's even student debates that are mock debates set up between students that address some of these misconceptions, and students have to pick which student in the debate they most closely align with. And these are Socratic, very carefully sequenced questions that allow students to work through their misconceptions by using plots and charts and different forms of reasoning to help support the more scientific way of thinking about certain concepts. And a little bit later in the presentation, there's a slide with additional resources and places where you can access think, pair, share questions, and lecture tutorials will be linked on that slide.
Thank you. And yeah, there was a question here about this recording is being recorded on YouTube right now because we're streaming it on YouTube. So you can watch it now or 5 minutes from as soon as it's done. And great point from Jim, telling a compelling story actually helps. Defining your terms along the way and linking to earlier concepts and analogs. Great points, great points. Next slide. So now we're going to take some of those things that you just heard from Sanlyn and Molly in terms of some of those tips, some of those ideas, and brainstorm together how to deal with things. So let's say you are at a table at a festival and people are walking by, asking questions, and you're talking, and an adult wants to know, why does Venus orbit the sun backwards? So clearly there's something here that they're not understanding correctly. What are some of the strategies that you might use to respond to that adult based on the strategies we just heard from Sanlyn and Molly? And Sanlyn was talking about short strategies. You might not want to do a whole hour-long lecture at this point. What are some things you might do to help answer that question that clearly is demonstrating an adult not really quite understanding how the planets work? Please just, so asking questions, finding out more. So one of Sanlyn's points was to ask the audience some questions. Please describe to me more what you mean about that. That's great, Bob. Thank you. Any other strategies? Sanlyn, what's something we should not do here at this point? What is a wrong strategy?
So this is my favorite. That's crazy. Who told you that?
Who told you that? I'm sorry, that's a ridiculous question. Shaming them, don't laugh or chuckle at their misinformation, shaming them, all of those things. Or just correcting it without asking any questions would also be a mistake. Good point, because it's going to go in one ear and out the other, and it isn't going to help at all. When I was asking the question here, an adult asked why Venus orbits the sun backwards, did anybody immediately start using their hands and kind of, okay, sun, Venus, and orbit, something that provides a visual and maybe a kinesthetic option where you're thinking about Venus going around the sun? And clearly, I've had people ask me about this or tell me that I did something wrong in a presentation because I didn't show that Venus went around the sun the other way, because they've heard that Venus rotates backwards, and they've applied that to their mental model of the solar system and assume that Venus is going the wrong way around the sun. So something maybe that uses a physical model where you're using hands or bodies to demonstrate what Venus is doing, that it's going around in the same direction around the sun as all the other planets, but it's spinning backwards. Might be another strategy that you could use. Anyone have any other strategies or things not to do? Because these are great.
And one of the things I always like to think about is, what is this an opportunity to talk about with them? Because clearly they're interested and they found something. And so I always like to think about, what is it that we can engage in to say, gosh, that's cool.
Mm-hmm. Gosh, it's cool that Venus rotates. It spins the wrong direction and so slowly. And how bizarre is that? And how amazing is that? Or the right way and upside down, all a matter of perspective. that Venus is either rotating the wrong way or upside down, either which is pretty amazing, right?
Right. And you can also talk about it. It doesn't have to be so case dependent. Like, we also have another weird planet in our solar system, Uranus, that spins on its side, and talk about how the same general laws of physics apply unanimously, despite some of these oddball planet cases. And so I like always having, something else that also supports a claim that I'm making. So now they may have their conceptual and reasoning difficulty cleared up about Venus, but if someone were to then ask them to apply that to a different planet like Uranus, if you can address the underlying issue, then they're able to take that understanding to any physical system. And I think that transfer of knowledge is really important.
Great points. Thank you both. And Jackie, it needs to be tuned into where the audience is saturated. So as soon as I start to glaze over, I wanted a quick answer to this one question. I'm already looking at the next table where they're handing out chocolate, and I'm not really paying attention. So absolutely good points. Take into perspective how engaged that person is with you in this discussion. Let's move on to the next scenario. So this one. You're in a crowded elevator, lots of people, elevator ride, so kind of short. And there's a 12-year-old who asks you about the moon landings and says that her father, standing right next to her, says that they were fake. Yes. How do we respond? What are some of the strategies that were discussed earlier that you can use in this response here? We'll give people a couple seconds to think about this and about wrong strategies as well. Let's see what evidence we have. So maybe talking a little bit about the evidence as a scientist and reinstating it's not just a matter of one person, what one person says versus what another person says, evidence, what data we have. That's great. Can you tell me more about what you mean? So that strategy of asking questions and asking for more information. I love that. remembering to do that. Any other strategies?
I think this is a really, if I may, Christine, I think this is a really good, silence is sometimes better. So I think because if you're taking this very literally and you're in an elevator and you really only have, 30 seconds, yeah, I really like what Joshua just typed up, but this is a really good scenario where you could take the piece of advice of letting people come to the conclusion on their own. So often what I do when I have a really brief interaction, especially because the father has a lot of lived experience that would allow him to believe that way, sometimes the best approach is to maybe provide the student or the family with a resource that they could go to on their own when they're not in the elevator to learn a little bit more about space travel to the moon. So I'd say, a great website that really talks about how we've traveled to the moon is X, or a really good educational video is Y. And then you would hope that obviously the family or the student who's interested or the child would take time to at least push their parents to explore. But if you really have a limited amount of time, sometimes it's nice to just have an idea of some handy resources to point at least the new generation in the direction of what's more scientifically accurate.
Great point, great points. And a lot of great quotes here as well. So thank you all. Let's go ahead and go to the last scenario before we run out of time here. You're giving a public lecture on Mars, not literally on Mars, you're talking about Mars. And one of the guests, a distinguished guest, asks why the astronauts didn't fall off it. They want to know why the astronauts didn't fall off Mars. Got a couple of misconceptions there. What strategies might you use for this one? You've got a talk, you've got an audience sitting there listening to you. Give them a visual of how things work on Earth. Thank you so much, Ed. So yeah, visuals are very helpful here. Ask them a question. Why do they think they might fall off? Why don't we fall off the Earth right now? So not shaming them, not saying, that's a ridiculous question. Everyone stand up and down. We don't fall off the Earth. There's another issue here, though. They just asked not only why did the astronauts not fall off, they asked why they didn't fall off of Mars. We haven't landed astronauts on Mars yet. But would you mind explaining why? So asking them maybe to reason a little bit. Asking more questions. It might be a language barrier. That's a great point, Ed. Sanlyn, Molly, do either of you have anything that you'd like to add to this, or other strategies that you'd recommend or that you would recommend not doing?
Go ahead, Sanlyn.
Well, I think, like I was looking, I think it was Lucy, this idea, or somebody was saying like, wow, we haven't even sent people there, but wow, we're very excited about it. And then thinking about, it's so great that we're thinking about what would happen. And then again, asking questions about why we think an astronaut might fall off, right? Just to start to think about what the underlying reasoning difficulty might be, whether it's about a flat planet or about gravity or about anything else, right? Flying off in outer space. But just, again, I always try and think about just turning it around to be like, we are super excited about what's going to happen, or we're very excited about the fact that humans may get to go to Mars, and then really thinking about that.
Right. Kind of like, well, humans haven't been to Mars quite yet, something like what Jennifer said, but our rovers don't fall off the planet because X, Y, and Z.
Our rovers don't follow. I had this question a lot back when I did planetarium shows, but they were asking about the moon and they wanted to know why the astronauts didn't fall off the moon. This idea that they didn't understand how gravity worked. They didn't understand that the moon had gravity. And I kind of shared, well, it's the moon has gravity, the Earth has gravity. If babies don't weigh very much here on the Earth, but they don't fall off the Earth. You don't have to be an elephant to stay on the moon. You could be smaller. You don't weigh very much, but you're not going to fall off. So yes, lots of questions that people might have asking about. From there, you might have a longer conversation about why the moon orbits the Earth, why how things work in space, how things interact with each other. And so you might need to do further discussions. One strategy, I would not recommend pausing your lecture and having a 10-minute presentation on gravity at that point. I would recommend having a short answer and then talking with that person after you're done about the rest of it and answering their questions and going into more details. Because, yeah, complicated, as Bob said. See me after the talk. Great point, great points. So sense of scale is good. Wonderful ideas here. Next slide, we have some resources. Molly and Sanlyn, do you want to speak just a tiny bit to these resources?
Sure. So the first two, the lecture tutorials for introductory astronomy, these are predominantly for practitioners, so in a classroom setting, but you could use think, pair, share type questions in a public talk. They've just been tried and true and tested in undergraduate lectures. But lecture tutorials, as I mentioned, they're in-class activities that are meant to supplement lecture on a specific topic. There's a whole book of them, and I linked it here. The third edition is already available on Amazon, but the fourth edition is about to be available in the next month or so. And these include updated tutorials and a whole new suite of planetary science-based tutorials. So planet formation, comparative planetology, terrestrial geology, that's all new in the fourth edition. And the Center for Astronomy Education website has great test question banks for think, pair, share questions, and also how-to guides for if you wanted to implement your own think, pair, share questions or create them, or your own active learning materials. So those are geared towards undergraduate classrooms, but could be used in a variety of public talk or classroom contexts.
And I'm kind of looking at, as we're going through this, I'm looking at a couple of the questions. And so do we have any resources that list old style catalog? Neil Cummings from UMaine actually, and I need to see if he still had it, used to catalog all of these and even made a book about it. So I will see if that is still available, because he had done that where he really listed like all the things my students really don't know. And so he had done that, and it was still active several years ago. We also have, and I'll let Christine talk about some of these other resources, some archived pieces from an old webinar done by people who are still actually doing lots of great work in this area, and Prather, Teresa Mooney, Janelle Bailey, and Georgia Bracey. And so we still have that archived, as well as a previous seminar that you've done.
Thank you. And yeah, the full PowerPoint that you're seeing right now is going to be available on our website under the Scientist Engagement website at LPI. It's not there yet, but it will be shortly. And so if you want to click on links directly from there, you'll be able to do that as well. And there were other questions and comments. Does anyone have a response in terms of a suggestion for a good ebook about Mars that somebody would like to share? Please enter it in the chat or say so. And there's a question about JMars, if anyone would like to answer that. And while you're doing that, I have one final evaluation question that I am going to put out there right now. And let's go ahead and move to the last slide at this point. We have a variety of these different seminars, and they're available. The recordings are available, the topics, and in many cases, the PowerPoints are also available at our website there that you see there. We value your feedback and your input about these tremendously. And so in addition to these two poll questions At the end of this, when you leave, there's going to be another website that's going to pop open with a couple of open-ended questions. We'd love your comments and thoughts and feedback in that as well. Sanlyn, Molly, do either of you have any final statements to make about any of this?
Just that I am happy to answer questions via email if individuals have deeper questions. Specifically, what I work on is undergraduate students. And so if you teach a general education astronomy class or even a more advanced astronomy class, you're looking for curricular materials or active learning strategies, please feel free to shoot me an email, and I'm happy to talk more at length.
I'd say, if you're interested more in kind of learning more again about how people learn, those types of resources, we will post those, but always welcome to chat about that for sure.
And one strategy that we didn't include is when you're working on your class, your lecture, your activity, whatever it is, reach out to an educational specialist or a member of that audience for their feedback while you're preparing. So that way we can help you and share some areas where your audience might struggle that you might not be aware of, some things that might surprise you. So I'm going to give everybody 5 more seconds to finish answering the poll question. 4, 3, 2, and 1. And I would love it if you all could help me thank Sanlyn and Molly for their time, and Grace and Sherelle and Yolanda for their assistance with today. If you have other things that you would like to hear more about, let us know. And Jackie's question, who you should contact first, it kind of depends. If you are looking for help specifically with something like teaching undergraduates, I would go to Molly first and then Sanlyn. If you are looking for Molly's more astronomy, planetary, Sanlyn or myself, and outreach, Sanlyn or myself. And we're delighted to help you. Thank you all so much. Have a wonderful day.